Since childhood, we're taught a very simple, intuitive rule about reality. If you drop an apple, it falls because the earth pulls it down. Sir Isaac Newton gave us this model, and for centuries we accepted gravity as a straightforward, invisible tether yanking objects toward the ground. There was just one glaring problem. When astronomers pointed their telescopes at Mercury, the planet refused to obey Newton's math. The orbit was off. The pulling force equation completely failed to explain what Mercury was actually doing in space. Albert Einstein looked at that exact same mathematical gap and proposed a radical solution. He claimed that gravity as a physical force does not exist. In his view, the Earth provides no pull on the apple and no pull on you. If there is no downward force, our basic understanding of movement disappears. We have to reconsider every reason why objects appear to fall toward the ground. Take a plastic bottle, poke holes in all four sides, fill it with water, and hold it steady in the air. Under Newton's model, gravity should continue pulling the water out of those holes as the bottle drops toward the pavement. Yet in a real fall, the flow of water entirely ceases midair. The droplets suspend perfectly still, hovering right next to the plastic as if they were in deep space. Because the water stops flowing, we know no force is acting on it relative to the bottle. The falling object has entered a state of perfect inertia, rendering it weightless and force-free. This lack of downward force led Einstein to a startling hypothesis. If the object itself isn't being pulled down, then the ground must be rushing up to meet it. This raises a massive structural contradiction. If people are standing on opposite sides of the planet, Earth would have to accelerate outward in all directions simultaneously. Logically, the planet should be expanding and tearing itself into pieces. To find the mechanism behind that acceleration, imagine you are inside a sealed, windowless spaceship floating quietly in the vacuum of space. While the engines are off, you drift. You float effortlessly in total weightlessness, experiencing that same state of pure inertia as the dropped water bottle. Then the thrusters ignite, accelerating the vessel forward. Suddenly, the metallic floor rushes up and violently slams into the bottom of your boots. Einstein called this concept the equivalence principle. The sensation of the metallic floor pushing against your feet is mathematically identical to the gravity we feel on Earth. The heavy sensation pinning you to your chair is the physical push of the Earth's surface against your body as it interrupts your natural inertia. But how can the ground push against us without the planet growing larger? We have to look at the four-dimensional fabric of the universe, spacetime. Massive objects like Earth warp this spatial grid, causing space to collapse toward the planet's center. Entering objects follow their natural inertia, riding these compressing pathways downward without any external force. This freefall continues until it hits a barrier. The dense, rigid surface of the Earth resists that spatial compression, acting as a permanent wall against the collapsing space. In a black hole, the matter is so extreme that the star cannot resist this inward spatial compression. The entire structure gives way and collapses. Earth, however, is solid enough to hold its shape. Standing on the ground means the surface is physically blocking your natural spatial freefall, providing a constant upward resistance against your body. We must distinguish this upward push from actual cosmological gravity. When you drop an object from a few feet high, you are observing apparent gravity. Drop two objects from 10 feet, their paths remain perfectly parallel. It's a local illusion. You only see the ground accelerating upward, but from 10 million feet, trajectories change. Traveling vast space-time, their paths bend and converge toward a single center point. This convergence is what real gravity is. It's the geometric deviation of parallel paths, forced together by the massive curvature of space. Our daily experiences are limited to a small-scale perspective. They hide the larger geometric structure of the universe that Einstein finally revealed. These two scientific paradigms offer two different worlds. Newton saw a predictable clockwork machine, while Einstein saw a flexible fabric yielding to mass. Newton's rigid model was a necessary approximation. It provided the basic mathematical rules required for us to navigate the entire solar system and understand the physical world. Einstein, however, provided the precise geometry of the universe. He proved that even when you sit perfectly still, the ground beneath your feet is actively rushing up to meet you.